Action.
Hello, my dear students. This is your Triboluminescence Lab. I've never tried to videotape this lab before because it involves some very low light conditions that I'm not sure that my camera can pick up, but we'll do our best. If not, try this yourself. All you need are some Wint-O-Green Lifesavers, and if you don't have any, come get some from me. It can't be old, and I suggest individually wrapped ones because if they're too moist, and things get moist in humid Arkansas, this experiment won't work. A crystal is a very ordered structure, and ordered structure requires energy to maintain that order. It's the same with your bedroom, it's the same with populations in biology, and it's the same with living organisms. We're very structured, and it's the same with crystals. And if you break and disrupt that crystal structure, it makes sense that you release energy. Actually, mechanically, as you break a crystal, you rub the atoms across the faces of the two broken parts at an atomic level and create friction, which creates heat, technically, so this could still almost be thermal, but that excites the electrons, and you also separate charges and other things happen, so that those electrons get excited, and when you separate charges and you create opposite poles, you may get a spark between them as well, just like lightning. What we're going to do is create lightning in our mouth. So when you do this experiment, you break the crystal structure of a Wint-O-Green Lifesaver by putting it in your mouth. Dry your mouth out best you can. Swallow all your spit. It even recommends using a paper towel to get it drier. Set it on a dry tooth. Keep your mouth open. Have someone come in close and look, or get in front of a mirror and bite. And you will excite the nitrogen electrons in the air and basically make lightning. A lot of that is not very visible, and so when we break the crystal structure of the sugar, we will transfer some of that energy to the methyl salicylate, the flavor of wintergreen, and it's a fluorescent compound. It absorbs light at one wavelength, which we may not be able to see, and re-emits it at a longer, less energetic wavelength, which we may be able to see. In this case, a blue, or some people see a blue-green light when they do this. Okay, so what I'm going to do is crush one in a pair of pliers, and I'm going to do this by taking the lights down. You need to dark adapt your eyes. I'm going to turn all the lights off in the room, and I'm going to focus on our corner of this table as close up as you can. Can you see the pliers now?
Barely.
Okay, we'll just have them in focus and don't move, because I'm going to turn off this light. If I can. There we go. And now we're in complete darkness. And on the count of 3, I'm going to, you can see the glowing glow sticks in the background from our last experiment. I'm going to crush it and see if we can see a spark. So, when you do this experiment yourself, I want to give your eyes a minute or 2 to completely dark adapt before you do it. So on 3, 1, 2, 3. Now I saw that spark. I hope it plays back. I'm going to start bringing the lights back up, and we will complete this lab with our discussion. But this is another way to excite electrons, to transfer energy to them and observe their characteristics. So if someone asks you, how do you even know electrons exist? Say, well, I can't see them, but I can see how they behave. And they behave as predicted according to the model. They exist in orbits around the nucleus. And when they move to a higher orbit, it takes energy to pump them up there And as they decay back to their ground state original orbit, they shed that excess energy as heat and light, and I can see the light. And not only that, that light is of a very specific wavelength corresponding to very specific quantized jumps of my electron. So when I capture that light and measure its wavelength, I can measure the energies involved. And we will be doing that later in this chapter. So our lab asks us to describe what you observed. And quite simply, and as bobcat purple as I can get, when the Wint-O-Green Lifesaver was crushed, light was emitted. You might even say a blue light or a blue-green light, whatever color you saw. I'm not sure what color I might have captured, if anything at all. Try it though, it's kind of cool. It's fun to do if you have some candy in a dark room. You can do it with other types of hard candies and when you disrupt that sugar structure, but the Wint-O-Green is the easiest to see. Now, the next couple questions are very simple. They ask you to define triboluminescence and fluorescence. And triboluminescence comes from the Greek tribion, to rub. As you rub those atoms across one another in the broken crystal phase, you excite them. And so, triboluminescence, spelled right there. If you look further down in your lab report, I have all these terms defined for you already. It's not chemiluminescence, it's not, thermal luminescence, but it's triboluminescence from the fact that triboluminescence occurs when the fracture or breaking of the crystal structure the energy released when you fracture the crystal structure stimulates, elevates an electron to a higher orbit, which then decays and emits light. As it sheds that excess energy as heat and light. And it's often of a very specific wavelength. Fluorescence is a phenomenon. There's a glowing gas inside a fluorescent tube. But it it glows in a gas discharge tube. Here's neon. But neon's expensive, and these require vacuum tubes and thicker wall glass and high voltage transformers. We excite that gas in a fluorescent tube, but it's not really in the visible range. So they coat the inside of the tube with substances that absorb that emitted energy and re-emit it at a longer wavelength that we can see with our eyes. So fluorescent lights, fluorescence is the absorption of electromagnetic radiation. So it could be in the ultraviolet, it could be outside of the visible range, but I'm just going to say is the absorption of light at one wavelength. Wavelength is the same as color. At one wavelength, and the re-emission at another longer, because of the law of conservation of energy, longer wavelength, okay, light has a smaller frequency or lower frequency, and so it has lower energy at another longer wavelength. I'm just going to finish my sentence over here. And finally, to complete our lab, it says distinguish between the energy source that provides the initial photon for the light emitted during a flame test and the source of energy in triboluminescence. We haven't done flame tests, we're doing those next. I'm getting a lab prepared and modified for virtual use for the flame test, but in a flame test, you heat something up in a flame. So, if I may, I need to erase this and move my screen so that I can have enough space to provide a suitable answer, but here are those definitions down here. So, in triboluminescence, energy to excite the electron is provided by fracturing, breaking, disruption of the crystal structure as opposed to the flame test, which we're going to do, flame ionization detection, or FID, in our next lab. Suppose a flame test where thermal energy, heat energy, is used, the heat of the flame, to excite the electron. This word here, it may not look like it, is the word electron. So, you can copy what I wrote exactly, you can put it in your own words, I might even give you extra credit if you do. And this is our second lab where we examine electrons and see their behaviors. We see them move out of their orbits into higher orbits and then move back into the ground state and emit light. We see these events occurring, and they all support our model for the atomic structure of the atom as, I guess, originally proposed by Niels Bohr and refined by other people, Schrodinger, and they were working on the information from people like Thomson, who discovered the electron, and Rutherford, who, saw it, gave us the nuclear atom. But again, we're looking at phenomena that are explained by our model for the modern atomic structure, the quantum model of the atom. I will see you in the next video. Goodbye now.